Hi everyone, this is Qing, and welcome to the third talk of Space West seminar. Today it's our pleasure to have Professor Salman Asif to give us a talk. And Professor Salman Asif received his MS and PhD degree from Georgia Tech, and he's currently assistant professor in the Department of ECE and University of California, Riverside. He previously worked as a senior research engineer at Samsung Research American, and he used to be a postdoc researcher at Rice University. His research interests includes computational imaging, signal image processing, computer vision, and machine learning. And besides that, Dr. Asif received a couple of awards, including the NASA Career Award in 2021 and Google Faculty Award, Outstanding Invention Award, and UC Regent Faculty Fellowship and Development Award, etc. And today, Professor Salman Asif will give us a talk on lensless imaging with programmable mask and illumination. We look forward to our talk. Thank you so much.
All right. Thank you, Cheng, for the kind introduction and invitation. Thank you, Sai. I must say that these kind of seminars or webinars are silver lining in pandemic, and I hope when we get back to the normal life, we can have some of this virtual component, which makes it easy for everybody to attend from different parts. So thank you for the invitation. Happy to be part of it. Today, I will present some of our some not so recent work on lensless imaging, using programmable mask and illumination. There are two main thrusts. There's one big thrust, which is on reconstructing the depth from these lensless measurements. And then later on, I'll talk about some recent work on illumination, on how we can improve the quality of images that we are reconstructing. Sorry, let me see if it works. So just one mandatory slide. I hope all the audience is familiar with these things, but just my take on classical imaging pipelines versus computational imaging pipelines. So in the classical imaging systems, we try to map real world scene onto the sensor as we see it, and centuries of work have gone into perfecting these cameras. Mapping is really designed to be identity, that as the image is present in the world, the light distribution that is captured on the sensor, and then all kinds of editing, enhancement happens in the post-processing, and that part is actually blurring some boundaries between what we call computational imaging, computational photography, and image processing. In particular, when we talk about computational imaging systems, really the real scene is mapped to a sensor as in the form of some coded measurements. The mapping that depends on the specific design that we have for the imaging operators depends on optics. In our case, it depends on mask, the placement, and pattern that we have on the masks, etc. And the reconstruction process really involves solving some inverse problems. Here in this figure, I'm showing this kind of pipeline that you have a scene in the world, 2D or 3D dynamic scene maybe. And then there's an imaging operator that gives you the measurements on the sensor. And we have to then invert that operator phi here, which is the imaging operator, to reconstruct the underlying image X. We have quite well, for something we have some strict constraints that parameters we cannot change, but then there are several parameters in this whole imaging pipeline that we have control over, and we can optimize or design it according to the application or task that we are trying to perform. When we try to do reconstruction, usually we utilize this well-known fact that images or visual data that we are interested in recovering belongs to a low-dimensional space, and we can exploit that prior knowledge to perform better or robust reconstruction. I will not get too much. I'll not talk about this aspect in the today's presentation, but if you're interested in it, we can talk about this offline. That what are different ways to learn this different representation model that we can use to improve the reconstruction quality. So today I'll focus on mainly lensless imaging. It is an example of computational imaging system. in which we get rid of lenses in the cameras. And the motivation for that is we want to relax maybe some constraints on the cost or weight or shape or area of the imaging devices. And that is done at the expense of computation, that if you do not have a lens that gives you a focused image on the sensor, then we have to sort of reconstruct that using computational algorithms. So today, first in this talk, I will briefly talk about what is flat cam, that how do we recover or capture images with these mask-based lensless cameras. And then I will talk about some of our recent work on depth estimation using flat cam. There are three sort of parts to it. One is that how we can recover an image or 3D image or depth and texture of the image using a single measurement or using a sort of fixed static mask. That is kind of what we did in flat cam kind of measurement. Then there are two more recent works. One is we are calling sweep cam, where we are capturing multiple measurements with a shifting mask, and the pattern is fixed in that case. And there's a very simple reconstruction algorithm that we can use to sort of sweep through different depth planes in the scene. And then the third one, it is a more recent work. I'm calling it Fourier cam in these presentations. We didn't call it in the paper with Fourier cam, but there the idea is, again, we are capturing multiple measurements with a programmable mask. And the pattern that we are using on the mask, we can learn using this sort of differentiable implementation of that reconstruction, which we are calling, in which we use Fourier diagonalization. And when I come to that, hopefully the reason for this term will be clear. And then last, hopefully I'll have time to get to it, is we have some recent work on using coded illumination to improve the quality of lensless imaging reconstruction. If during the talk, if you have any question, please feel free to stop me, and I'll be happy to discuss those things in details. So what is flat cam? It is a bare sensor with a fixed binary mask placed on top of it. So a CCD or CMOS sensor, like you see here in this figure, we have exposed that that sensor, and we have placed a mask, a binary mask on top of it. The transparent regions that you see in the mask, they are, oops. So binary means that there are some transparent regions, and then there are some opaque regions in this mask. And if whatever scene you have, you put in front of that, and then you place that mask at a certain distance from the sensor so that you get some multiplexing. If you place some scene or whatever scene you have in the world, light from all the pixels from the scene will come towards all the pixels on the sensor, and we will get a sensor measurement that may look like this. This brownish or rectangle that you see here. And there are some details that I'm not going into that we can need to calibrate, that what is the mapping of the scene onto the sensor. In this flat cam paper, we assume that the scene is planar and mask has a separable pattern. So we get a separable linear system that represents any light distribution that we have on the scene, mapping of that onto the sensor. And then we can invert it using some simple, say, regularized least squares kind of methods. So that is what we did. That was around 2016, 17 timeframe. This idea of using masks or coded apertures, if you will, to capture images is not new. That is a classical approach people have been using in high energy imaging, X-ray, gamma ray imaging systems, where there's a physical sort of limitation that we don't have any material that can bend light's waves at that high frequency. So you need to use these sort of lead plates to block some light and then allow some light to transmit. The problem formulation in principle is very similar, that you are getting an image, you have some coded aperture, you are recording some measurements on the sensor, and then you need to invert that process. Some of our motivations when we started working on the flat cam, or even now for some ongoing projects, is that we want to make cameras that are extremely thin or flat. That most of the existing cameras, they have this cube form factor. You need to place these, even in those original coded aperture systems, you need to place the mask sufficiently far away from the sensor so that you get this either convolutional model, or you get you get, in the case of lenses, you put it far away so that you get a sharp focused image. If you want to break that cube form factor and make cameras that are really thin, flat, then we can't put lenses on the cameras. So that was one motivation. If you want to make cameras that are maybe flexible or sort of distributed on kind of some surfaces, we do not necessarily have these optics, or making those optics that can focus on different arbitrary shapes is not a trivial task. Or more recently, some of these things, like people want to put cameras under the display, so you want to make everything thin, you can't afford to have lenses, and etc. So that was the main motivation for looking at these mask-based imaging systems. Some kind of illustration of the main idea, that why or how do we get an image from these mask-based measurements. So what I'm showing here is illustrating a point source that is moving in the scene. So that animation stopped for the left figure. I don't know why. But the idea is that if you have a single point source and then there's a mask in front of the sensor, as you move the point source, the shadow of the mask changes. So that gives us this idea, this model that every point in the scene casts some shadow of the mask onto the sensor. It is nearly shift invariant. We don't have to sort of necessarily model it that way, but the main thing is that sensor essentially records a linear combination of light distribution over an entire plane, if you're assuming that this point source is moving in a plane. And we can model this mapping of light from a plane onto the sensor as a linear system. And then we can, like I said, we can just invert that linear system and reconstruct images. Here are some examples of some earlier results from that original FlatCam paper. On the left side, you see images where we're getting one static scene, and then on the top, you're getting some measurements on the sensor. On the bottom, you're getting the reconstruction. On the right-hand side, it is like there's a moving scene, and you're capturing multiple frames of that scene, and you are able to reconstruct the video as well. So that is old stuff. On this slide, I'm trying to illustrate this idea that you can actually, the depth information is also encoded in the sensor measurements, and the reason behind that, which again animation stopped, is that in the case of planar, if you have a single scene, as the point source was moving left to right, then you were getting shift of the mask. If the point source starts moving towards the sensor or away from the sensor, then you get a scaling of the mask. So the scaling of the mask is encoding the depth information. So in short, every point in a 3D scene also casts unique shadow at the sensor. Sensor again records linear combination of the entire 3D scene. If you have a single shot, single sensor set of sensor measurements, this is a highly underdetermined system because you are getting 3D scene light from the entire scene is mapped to a single frame of the sensor. We can model this mapping from the scene, or if you think about the scene just has a surface and each point on the surface has a certain depth. We can model that as a linear system, but it is linear system only if the depth is known. So if we do not know the depth, even if it is a single plane and we do not know its depth, it is not a linear problem. We need to estimate the depth because depth is another unknown parameter, because that determines the mapping, the forward operator. So just the main takeaway from this observation is that depth recovery is it is a feature of this lensless imaging system, but it is also a necessity, because if your depth estimate is not correct, then there will be a model mismatch and we will get some artifacts in the reconstruction if we just model it as a linear system. In recent years, there have been several works on reconstructing depth from lensless cameras. I'm just putting two of the popular ones and then some recent work from my group. So this diffuser cam and this flat scope from diffuser cam from Berkeley, its flat scope is from Rice. They try to solve this 3D recovery problem from a single shot by modeling the problem as the forward problem as the linear, where you're mapping a 3D volume onto a single sensor frame. And then there is some regularization, some assumption about the sparsity of the scene that for which you need to solve some L1 regularized or some structured inverse problem to reconstruct the 3D volume from a single measurement. What we did in this work with my student Yuzheng is that we modeled this reconstruction problem as a non-convex problem where we want to jointly reconstruct the intensity of different rays that we are getting on the sensor and the depth of those rays. So in that way, the problem becomes non-convex, and overall, all these are underdetermined, but we were solving this non-convex and non-linear problem. So I'll go through it quickly. If there's, again, any question, feel free to put it on the chat or ask it. On this slide, I'm showing an overview of our depth recovery or this joint image and depth recovery process that you have 3D scene. We are just showing you the different side views or front view of that scene. You're getting one shot on a sensor. You have a fixed mask. You're getting one sensor measurement. The captured measurements may look like this. Then we have two steps. One is this, what we call a greedy algorithm. I will not go into the details. You can read it, look at that in this paper or talk to me offline. Main idea is that we first do some coarse discretization of the scene into some finite small number of depth planes. We estimate the intensity of the light rays that we are getting from different angles, and then we assign them one of the depths in those depth planes. And then we solve this sort of alternating gradient descent problem where we try to fine-tune the depth for each ray along with the intensity information from each ray. So that is how we solve this continuous 3D reconstruction problem. This is the model in a gist, in a nutshell, that the main thing to take away is that this is kind of illustration of the imaging setup in 2D space, where you can think about this vertical axis as the depth. The horizontal one is telling you the space, and it is X or Y, both of them. You can think about it that way. So this blue plane is a sensor, the red plane is a fixed mask pattern, and we are discretizing the scene in these uniform angles. So angles in the horizontal and vertical direction in the 3-dimensional space. And then depth is discretized in this inverse depth space. They're also called diopter space. There is some relation between the point source at any point in a 3-dimensional space, that what sort of sensor measurements or the mask shadow that we get, or point sprint function, if you will, that we get on the sensor, that is encoded. All of that is encoded in this operator. That there is a depth-dependent forward model for representing any measurements that we observe on the scene, where L is representing the intensity of different angles, and alpha, it's again a vector or object of the same size as the number of pixels you have in the scene, that is encoding the depth of every ray in the scene. So our goal is to recover the intensity, this sort of vector L, which is as many as the number of pixels in the scene, and the corresponding depths, which is encoded in this alpha parameter. So this is a non-linear inverse problem. We solve it using sort of standard alternating gradient descent, where we minimize the loss between the observations, Y, which is a single sensor measurement, or single frame of the sensor measurement, and then this approximation from the forward model, and then some regularization on the depth that you expect that natural scenes that we see in the world, they have this smooth sort of piecewise constant or piecewise linear depth, and that is the kind of regularization that we used. I'll show some results here. So on the left-hand side, you see these are simulations. So this image is one of the Middlebury images. You have intensity or texture on the top, depth at the bottom, and then I'm showing some reconstructed images from a single shot which just demonstrate that depth reconstruction is possible. And we try to use different regularizations, so TVL1 or weighted TVL2, where the weights we did some kind of bilateral weights, and that was overall giving us the best performance, and that's what we used. Here are some additional simulation results. The main takeaway from here is that as you increase the size of the sensor, area of the sensor, so in this case, we use the same number of pixels, but we increase the size of each pixel. So that increases the area of the sensor, which gives you better baseline, and that improves the quality of reconstruction. But if you make the sensors bigger, then sensor pixels bigger, that also sort of has some effect on the quality of reconstruction. So intensity is quality of intensity takes a small hit, but depth reconstruction is it improves. We can overcome that by increasing the resolution of the sensor, taking larger sensors and increasing the number of pixels, which adds to the complexity of solving this inverse problem, but that is the trade-off we have to work with. So main takeaway is that, or main lesson we learned was that, at least in simulation, reconstruction is possible and quite robust under different scenarios, different sort of scenes that we simulated, or different noise levels that we simulated. One thing I will add here, these kinds of lens-based or lensless cameras, the range in which they give good depth is very limited. So the range in which they give good depth is proportional to the size of the sensor that you're getting. And really, these sensors we use, they are 1 to 2 centimeter wide at most, and the range in which we get good depth estimation is anywhere from, say, 1 centimeter or few centimeter to tens of centimeters away from the sensor. So within a meter, maybe, or half a meter, if that is your object, you can get good depth. But if there is any object beyond that, then it is at infinity for the sake of lensless imaging. So depth discrimination window is really small. So here on this slide, what you see is that we tried simulating scenes that were like few meter, within a meter, or tens of meter away. So like if something goes really far, then that scene will appear at the same depth for the lensless camera. So those results are simulations. We built a prototype to test this algorithms. Here I'm showing on the right-hand side some snapshots of that prototype. So this green PCB you see, that is the exposed sensor. I don't remember the details of the sensor, but we used effectively 512 by 512 sensor measurements. Effective sensor area pixel is 11 sort of micron, and we are calling it effective because we binned some of the pixels to group multiple pixels into one macro pixel. And this sort of transparency that you see in front of that camera, that is the mask pattern. So there's a mask pattern printed on a transparency. This is the plastic transparency. We just place that transparency on top of this exposed sensor, and that is our mask or mask-based or lensless camera. And then we had different kinds of scenes placed in front of the sensor. So they're all quite challenging, that you have the slanted plane with some texture on it. You have multiple slanted planes, or this kind of diffused kind of a statue. And what you see, the results that you see, they are coming from 3 different methods. Ours is this reconstruction from the algorithm that I just explained. Greedy is that initialization method that I briefly discussed in the beginning, and then 3D grid is one of the methods where we impose the sparse regularization on the 3D volume. So it is reconstructing the 3D volume of this from the scene, and then we are selecting the pixel that gave us the maximum intensity and making a surface from that to show this 2D image and the depth estimate. Main takeaway is that if the depth estimate that your methods are giving you is incorrect, then you get artifacts in the reconstruction. That is what you see in the reconstructed images when the depth estimate. So depth estimate are the second rows, and then reconstructed intensity is the first row. And then from our method, depth estimate, we don't have a quantitative measurement of how good the depth estimate was, but visually, here in this setting, the bluer pixels are closer to the sensor, the reddish pixels are farther away from the sensor. So qualitatively, we observe that we are reconstructing close enough depth. And that was reflected in the quality of reconstructed images that we got, that resolution was better. We had fewer artifacts in the reconstruction. So those are some of the main results from this work, where we try to reconstruct 3D, continuous 3D from a single shot, single frame of the lensless measurements. So if there's any question at this point, I can pause.
There's a question. So
sure.
The question is, can multiple, for example, two sufficiently spatially separated lensless sensors be used to improve depth perception?
Yes, definitely. So I had a paper in some ICASP early on, I don't know, 2017, 18, where we simulated this process that, if you have multiple sensors, we wanted to make some different shapes of the sensor using different lensless cameras. And in simulations, it worked beautifully. It was not a very exhaustive or realistic simulation because we did not do dense sampling. But yes, if your baseline increases, if you put two lensless cameras far away, and then you need to calibrate their correspondence the way we do in the stereo. Somehow you need to reconstruct the same sort of voxels using these different measurements. And as long as that can be done, your reconstruction quality will be better than what we are getting with a single small sensor. Yeah, that's a good question. Okay. If there's no question, I'll go to the second sort of part of the presentation, where in this one, I'll talk about the sweep cam and Fourier cam, where we are trying to recover 3D or perform 3D lensless imaging using multiple sensor measurements. So there will be more than one sensor measurements that we'll use to reconstruct the 3D scenes. That part is mainly, these are two papers. So one is sweep cam that was in PAMI last year, and then the other one, I don't think we had the Fourier cam in the paper title. I'm just putting it here now, but this simple framework for 3D lensless imaging that was presented in ICCV last month. And most of the work on this is, or on the sweep cam, was by Yi and Ashwin from CMU, so it was in collaboration with them. And then most of the work on this ICCV paper was by Yu Cheng, who is my student at UCR, in collaboration with folks at CMU. So here in this case, when we try to perform 3D lensless imaging with multiple measurements, we assume that the scene can be discretized to a certain number of parallel planes. So that was kind of one model that we assumed. The second one is similar to what we have in the first case, that if you have any mask pattern, that the other thing, the multiple measurements aspect here in these two examples is coming from the fact that we are changing the mask pattern. So in the case of sweep cam, we have a fixed mask pattern, but we are shifting it in the plane, in the mask plane. In the case of this second method, what we call Fourier cam, we use this programmable sort of mask in which we can change the pattern of that as well. So that is where the multiple measurements are coming in. So if your mask pattern for any given mask pattern, the forward model is same as what I discussed earlier, that sensor measurements are this convolution or depth-dependent convolutions of the scene and the mask pattern. So that is what the forward model looks like. Mathematically, we can represent it this way: that for a fixed mask pattern, that is, say, this texture, this binary pattern we see shown in this block, for different depths, that mask pattern will either shrink or expand. That is the effect of different depths. And the measurement that you record on the sensor is the convolution. So the other thing, which is slightly different from flat cam, is that here we are using a convolution model. What it means is that you have to assume a certain spacing between mask and sensor, or you have to assume that the scene has a very small field of view. So under those assumptions, we can treat the model as a shift invariant model, and that is what we can model with the convolution. The sensor measurement is recording depth-dependent convolution of the mask patterns with different planes in the scene. So here I'm just showing two planes that this say mesh. If this is your 3D scene where duck is at one depth and then this sort of mesh is at a different depth, you are getting convolution of this mesh with a scale version of the mask. Then you are getting convolution of this duck with a different scale version of the mask with the intensity, and summation of that is the sensor measurement. If you change the mask pattern, the scene remains the same, assuming that the scene is static in that entire acquisition process. The mask pattern is changing, and that gives you a different sensor measurement. And we captured multiple sensor measurements. That gives us enough sort of diversity in the overall sensor measurements. And we can use afterwards, we can use all the sensor measurements to reconstruct the depth. And I will discuss two different ways of reconstructing depth. One is with sweep cam and one is with this so-called Fourier cam. On this slide, it's my attempt to simplify the math. I don't think I can do justice to it. You can see more details in the paper. What I'm trying to show here is that this vector L is the scene intensity at different depth planes. And then Y is different snapshots that we are getting with different mask patterns. And the C of phi 1, 1, or with two subscripts is the depth dependent convolution matrix. That is the first mask pattern depth plane 1, first mask pattern depth plane D. And then at the end, it is the kth mask pattern with depth plane 1 and kth mask pattern with depth plane D. So these are convolutional matrices. So motivation for sweep cam was that can we sort of make this 3D imaging problem well determined, and can we reconstruct one depth plane, and we can reconstruct that one plane with a clean and good resolution. So we wanted to just focus the image on that depth plane without any lenses here. So we wanted to combine lensless measurements so that we can achieve the focus. So that was one motivation. How did we do that? In the case of sweep cam, we captured multiple sensor measurement by shifting the mask pattern. So it was a fixed mask pattern that we are just shifting to capture multiple measurements. And we can recover, the main idea is that we can recover one depth plane by shifting, adding, and performing a simple deconvolution on all the sensor measurement, on one sort of combined sensor measurement. So the reconstruction for a single depth plane is super easy. Mathematically, what it means is that we kind of ignore, we assume that all the measurements that we are capturing are actually observing a single depth plane. And under certain conditions, it actually works out that mathematically you can think about it in this way, that if these systems that we are getting different system for different depths, if they were kind of orthogonal to each other, then we can recover depth for each plane independently. So that is the main idea. So in the sweep cam, we just select one depth and ignore the rest. We solve one system of a small size, and computations become very simple because of the shifting property of the mask pattern. That in the case of sweep cam, we are capturing first sensor measurement with a fixed mask pattern, and the second sensor measurement is captured with the same mask pattern but just slightly shifted in the mask plane. So we move the mask pattern and we capture multiple measurements, and then we can reconstruct the different depth planes. So before going to the detail, let me try to illustrate that using the simplest mask we can imagine, and that is just a pinhole camera. So you have, or just a pinhole mask. So here you have this sort of mask with a single hole that is just a pinhole. You will get one-to-one measurement from the scene to the sensor. That is what we observe in this image on the left side. You have, suppose your scene consists of two planes, one is near, one is far. So what you will see is that if I move the mask, then you will see a depth dependent shift of different planes onto the sensor. So if we move the mask pattern, the plane that is closer to the mask will shift more than the plane that is farther. So there's a depth dependent shift involved in this mapping. So this is, if you just imagine that a pinhole is moving, you will get these three different stacks or different sensor measurements with sort of different shifts of different image planes. How we can recover one depth plane? Well, the idea is very simple. We can just align all these measurements according to the depth that we want to recover. And we can just average. What it will do, it will give us a focused image of the depth plane that we are selecting, and it will kind of blur out all the other depths that we did not select. So that is the main idea. That if we want to focus near, we just align the sensor, shift and align the sensor measurements according to the near depth. If we want to focus on the farther depth, we align and add all the sensor measurements according to the farther depth. And with a single pinhole camera, that is the solution we get. If you do not have with a pinhole mask, that is the solution we get. If you do not have a pinhole mask, you have some coded mask like we use in the lensless cameras, then the process is similar. I cannot, I thought I can go through this math, but I'm going slow on time, so I will not attempt that. The main idea is that because of the shift operators, because the mask is shifted, same mask, just shift different shifts that we are enforcing in this, and shift is commutative, so we can assume that we are shifting the scene and then use the same mask pattern to perform deconvolution. That's the main idea. What we do in practice is that we just align the sensor measurements according to the same shift that we saw in the case of pinhole camera. We average. That gives us this sort of sensor measurements that are now corresponding to the image that is focused on one depth plane. So in this case, focused on the near depth plane. If we align and add the measurements in a different way, you get the sensor measurements that are focused at a different depth plane. And the computation, the main computation we need to do is just one sort of Wiener deconvolution on a single sensor measurement. So in this case, you take the mask pattern corresponding to this near depth plane, you perform a deconvolution with that, and you get this reconstructed image, which is focused on the near depth. You take a different mask pattern, use this modified sort of accumulated sensor measurements, and you reconstruct the focused reconstruction of the plane at that farther depth plane, and nearer depth plane will become blurred out. So that is what we have main procedure in that sweep cam paper. And here it's an example reconstruction that we have this the scene. Again, the range is quite narrow, the depth range in which we can recover these and discern these different depths. So 4 to 14 centimeter, there are these toys which are aligned or arranged in this manner, and we can sweep through these depths by selecting different from the same stack of measurements. We can select different depth plane and perform this focusing operation. Okay. Here are some more examples. Sorry, question?
Yeah, I had a quick question.
Yes.
Is there a way to use the information you collect to do sort of a more continuous focusing?
So this focusing is continuous in the sense that we are not doing, I'm showing you a finite number of depth planes, but you can select any depth plane and you can recover it.
I see.
If that is what you're saying about continuous focusing.
Right.
Yeah. So that is what is happening here.
Mm-hmm.
But ultimately, the quality that whether you can discern one depth plane from the other, it depends on the number of measurements that you're getting and the scene that you have. So that part depends on other factors, but computationally, you can select any depth plane.
Right. So I think my question was the latter, if you can infer.
Yeah. That depends on how big the sensor is and how many measurements we are capturing, and whether this convolutional model is valid in that range.
Mm-hmm.
Yeah.
Sounds good. Yeah. Thanks.
All right. So here it is showing some examples of reconstruction for different scenes. So this is again a slanted plane, and you can see the number of measurements here. It is like 19 by 19 shifts of the mask, means that we're getting almost 400 measurements for this scene. So there was a lot of measurements were needed for this kind of reconstruction. On the left hand side, you see that what would happen if you have a single measurement of the mask with a static single measurement of the scene with a static mask. or even multiple measurements where the mask is static, and then you try to do the sweeping. So sweep is not, you can get some of that effect, but your focusing or that desired artifact-free reconstruction of different planes that you want is not there with a static mask. Here I'm showing some comparison with like this earlier paper where we can do this greedy reconstruction with depth estimation. So we can recover some depth with a single shot, but it is not as clean as what we get if we have hundreds of shots and we perform this sweeping operation. Some more examples. Main takeaway is that we can do this depth sweep in a reliable and robust manner. So that was the sweep cam. We captured multiple measurements while shifting the mask pattern. The algorithm is fast, and when we want to reconstruct each depth plane separately, we can do that. But a good reconstruction would require a very large number of sensor measurements so that we have enough space to shift the mask and then cancel out the effect that we are getting from other planes that we do not want to reconstruct. So from here, and looking at this sort of model, we had this modified or revised sort of way of reconstructing the or performing this 3D reconstruction. And the idea is quite simple: is that all these systems that you see, they are convolutional. From signal processing first course, we know that we can diagonalize these convolutional operators using Fourier transform. So that is what we can do, that we can just apply a Fourier transform. And what happens is that this very large sort of big block circulant system or block topilar system can be diagonalized into a block diagonal system in the Fourier space. And what it means is that if you have n sensor measurements and you're assuming that the scene consists of n pixels, and we capture, say, this capital K snapshots. The other thing, again, we assume that the scene, in this case, we need to assume that the scene is, say, discretized into a finite number of depth planes. So if suppose you have D depth plane that you want to discretize the scene in, and what discretization you want, that is in your control. That how far, how refined you want to do and where you want to place each depth plane, that is in your control. But at the end, what we can show is that this overall system, we can actually represent that as n parallel systems. Each of them is of size k by d, where k is the number of sensor sort of mask snapshots that we are getting, and capital D is the number of depth planes that we are assuming in the scene. And then we can just implement this this using very fast implementation in some
Hey, Cheng,
Is it stuck?
yeah, I think we lost Salman. Hopefully he'll join back.
Okay. Let's wait for a second, for a minute.
Hi, sorry,
Hi,
I don't know. Was it from my side or? My apologies.
Sorry.
I didn't do anything.
We can resume from where.
Okay, I need to find my
Slide.
here slides. Okay, do you see my slides?
Yeah, we can see your screen.
Okay, and I'm on the correct slide.
Yeah.
Okay, my apologies. I don't know what happened.
Problem.
Okay, so the forward model is the same that
I think sorry, Salman. So I think you need to maybe full size your screen for the first slides. We can see.
What do you see?
We're seeing your screen, but it's not your the full size of your PowerPoint. Oh, yeah, this works. Yeah.
Oh, okay. I see. Okay. All right. So yeah. So up to this point, this is sort of I'm representing this this forward operation where you are capturing multiple measurements of the scene by changing the mask pattern. So here it shows the 3 images. So those 3 images are captured with 3 different mask patterns. And then we can perform the Fourier operation on those sensor measurements and get those independent small systems. That is what I'm trying to highlight here. And we can perform reconstruction over each of the depth planes. So in words, you are trying to reconstruct every frequency for all the depth planes. So that is what we're doing. And from that, we can then reconstruct perform the inverse Fourier transform, and we can reconstruct the intensity on the D depth plane that we are trying to recover. The interesting thing about this framework is that what we did actually later on was that we put it and implemented in PyTorch that everything is differentiable, and we can actually optimize over the mask pattern that that gives us the best reconstruction of the plane that we are trying to recover. So that second part of this work was that we were actually optimizing over the mask pattern, and then that did provide us good reconstruction, improved reconstruction in the simulation and also in the prototype that we built. And second part was that once we have these depth planes, there are still a finite number of depth planes. We can train a simple UNet kind of architecture, which takes these small number of depth planes and give us a continuous depth map and fuses all the intensity from different depth planes to give us one all in focus image, if you will. So those are some details. I mean, here I'm trying to highlight that, yeah, we did this iterative process, back and forth, back propagation, and implemented in as kind of a differentiable network and optimize over the mask patterns. The loss function decreases, we get different mask pattern, and the reconstruction that we get from those optimized mask patterns is better than kind of the initialized mask pattern that we used in simulation, and we observed this effect in the prototypes as well. I was not in the camera prototype. Main thing is that there's a programmable mask here. It is a spatial light modulator. Rest of the setup is very similar. There are different values for the parameters for the number of sensors and spacing, etc. But let me come to the main results. So on this slide, I'm showing you a comparison with sweep cam, for instance, and this so-called Fourier cam. So in the case of sweep cam, like I said, the original paper we did, we had many measurements. If you try to reduce the number of measurements, like we are doing here, that we just take 8 mask patterns, then we do get some sort of depth selection or this focusing, but it is not as sharp as we saw with hundreds of images. Whereas if you jointly reconstruct all the depth planes that we did in this Fourier cam, you get a very fine and very sharp results. What we see here is that in the beginning, when depth plane that we are showing is smaller, you are focused on the mesh. Then as you go towards the deeper depth planes, that mesh kind of blurs out and you are observing the duct that was behind this mesh. So that is the result that we see here. Similar thing in this experiment where you have 3 toys. Sweep cam is doing good, but it's not doing as good as what we are doing with Fourier cam with the small number of measurements. That at a smaller depth, this blue toy is in focus, then you focused on this orange toy, and then at the end you focused on this white toy in the background. And that shows us that we are performing good depth selection and then reconstruction. Some more examples showing the same effect. I will let it run through one loop and then move to the next part. Here's a comparison between the different types of mask pattern that we tested. So on the left side, you see the separable mask, MLS mask that we actually used in the case of sweep cam, and we experimented with that same mask pattern with this sort of joint reconstruction. So results are not as clean or good. With the random mask patterns, it had some artifacts as well. And the learned mask pattern that we got from our method provided us the overall best results. And that is what you see on the right-hand side. Color, there's some color mismatch. That is because of some post-processing we did to remove, to make everything consistent for each given mask pattern. So we can make we can make all of them same color. So that color mismatch is not a big effect. The main thing is that we are getting better depth selection with the learned mask patterns. Just quickly, these are some results that we got when we sort of passed on the right-hand side, when we passed our reconstructed stack from the strained unit kind of method. We get reasonable. We don't have a quantitative comparison of depth reconstruction, but qualitatively, yeah, these more yellowish regions are the ones that are closer. Bluish are the ones that are farther, and no, yellow is the farther and blue is the closer, and that is what we see qualitatively. On the left-hand side, it is another method. You can see more details in the paper where we try to do some kind of hand-designed local contrast method to assign different depths to each pixel. And that was doing well, but then this depth refinement-based, unit-based refinement was much better.
Hi, Salman. I want to ask a question. Because to learn mask, how do you, I mean, the mask should be given before you do the sensing, right? How do you learn the mask?
So we did it on some NYU dataset. We learned the mask pattern using this implementation of forward model and then reconstruction in some PyTorch environment. And the reason we can do it is because we are not solving a very high dimensional, complicated inverse problem. We are solving very simple inverse problems because of this parallelization.
I see.
Yeah. So it was, that was, sorry,
minimization of your signal and the mask, or do you do them separately? Or?
Oh, so when we are, so the way we are training is just up to this part where we reconstruct some depth planes, and the original NYU dataset is actually discretized on the same depth planes.
Oh, I see.
So we compare the reconstructed depth planes with the original sort of ground truth depth planes. And that becomes our objective. That is the loss we want to minimize while optimizing over the mask parameters. So the reconstruction algorithm is fixed. It is a function that takes your sensor measurements, spits out your reconstructed images. So that is not trained or learned. The only training is happening in this first half is only on the mask pattern. So those are the optimization variables.
Oh, I see.
Yeah.
I have a related question.
Sure.
In practice, are these masks how hard is it to program the actual mask, the hardware? Can it be like is the technology there that you can program them in real time?
Yeah, that's so I think that technology is there. So this SLM, spatial light modulator, they exist. These are phase SLMs. You can buy. They're expensive, but you can buy and put them there. The main question is whether they are cheap enough to put it in this lensless cameras. That answer at this point is no. So this programmable mask pattern, when you're completely changing the pattern, that one will, I don't know if that technology is there, but if you want to just shift the mask pattern that we did with sweep cam, or we can use the same idea in this sort of diagonalization operation with the Fourier cam, that can be done. So you can put some, well, I hope it can be done. I don't know much about optics from that side, but I've heard that these are these piezo stages that you can use to sort of shift the patterns, but I'll stop at that because we are live and I don't want to give any misinformation.
Sounds good. Thanks.
Oh, sorry. Go ahead, Si.
Oh no, I'm done. I just said thanks.
Okay. I see.
There's a couple of questions from the audience. So there's three questions. I think you can address them one by one. The first question is, could you please comment on the computation burden of these methods? How much time does it take to reconstruct an image on a certain processor?
So that answer is simple. We are solving, so in the case of sweep cam, we are performing some summations and interpolation. So whatever is the cost of interpolation for an image plus the cost of a single deconvolution, which can be done using 2 Fourier transforms. So it's the cost of few Fourier transforms. In that Fourier cam paper, it is parallelized. So each node is solving a small system, so K by D. In our experiments, we were doing a 10 by 10 system. So each of that can be solved very efficiently, and you want to solve n of them in parallel. So if you have a reasonable, like a standard GPU, you can perform that reconstruction quite efficiently. So both of them, sweep cam, Fourier cam, they are extremely fast. The first one I presented, the joint estimation, that takes few minutes because you're solving. And the main cost comes from the forward operation in that.
The second question is, how about where there are moving objects?
Yeah.
In imaging
Yes.
natural things, they always exist.
Right. We are working on that videos. These results are on static images. So yes, if your scene is changing and you are not incorporating that information in the model, then there will be some mismatch. And third one, I think, is related, that it's feasible for video, or related in the sense that, yeah, we are working on it, but we don't know the answer right now.
Got it, thanks.
Yeah, thank you. I need to then close this question tab. So I will not take very long for the last part. It is pretty short. It is some work that we have been doing for lensless imaging with coded illumination. And for this one, there were two motivations for us. One was to improve the quality of reconstruction. And second one, like I said, it was the main application that motivated this work was putting the cameras under the display where you have illumination from, say, the displays available to you. So that was the main motivation, that we can actually illuminate the scene with different patterns, and then we can use those patterns along with that sort of mask, forward operation from the mask, and we can get diverse set of measurements and then get better reconstruction. There are some details, other details here that you get very interesting and nice sort of structured in the forward and inverse problems. I will not go into that. We will post this paper soon on our website, so you can take a look at that at that time. Main thing takeaway is that this example reconstruction, that if you have a single sort of mask, that whatever lensless camera you're picking and you're just illuminating the scene uniformly, that is what we conventionally do. This right side image is what is the best reconstruction that we can get. And if you have some coded illumination setup available, then you can improve the quality of reconstruction by a large margin. And that is what this slide shows qualitatively. In experiments, the way we set it up, we had a simple sort of laser projector with which we were projecting some patterns. And some patterns that we found were extremely useful. One of them was this shifting dot pattern, that you just have a fixed dot pattern and you are just shifting it around, and you're capturing multiple measurements with that. You can use any other sort of orthogonal pattern as well that gives you orthogonal bases on a small patch of the scene, and that works as well. I'll just quickly go through some experiments and some results. That on the left-hand side, you see the camera view. The second column, you see reconstruction, best reconstruction we could get with a single illumination pattern. And then as we are increasing the number of illumination patterns, which means you are capturing multiple measurements, the quality of reconstruction improves and improves quite significantly, that we see on the right-hand side. Here's an example of, so on the previous slide, it was images that we printed on a piece of paper and we just placed that on a black background. Here, there were some real objects which have some depth variation. In this setup, we are just assuming the scene consists of a single plane. And we are not trying to reconstruct depth. And we are just trying to observe the improvement in the quality of reconstruction. And we see that as you increase the number of illuminations or measurements, the quality improves and improves quite significantly. So one potential application of this kind of illumination can be in the setup when you do not have a large sensor, when the number of measurements you have on the sensor is small. And that is what we try to simulate in this case, that if you start with, say, 512 by 512 sensor, but then you are binning, or you are starting with, say, a small sensor that only has 64 by 64, say, pixel, then you want to recover 128 by 128 or 256 by 256 scene. So the system is already underdetermined. If you provide some additional measurements by capturing few coded illumination, by capturing measurements with different illumination patterns, we can work with that otherwise underdetermined system as well. So that is the main takeaway from this slide, and some results which show us that illumination-based reconstruction is quite robust to even even large binning, or the setting when you have very small size of the sensor. So with that, I will stop. Just a quick summary of depth estimation. Like I said, at least when we have a single shot, is a feature and also a limitation or necessity for lensless imaging. We either need to solve nonlinear inverse problem with a fixed mask to estimate the depth, or solve that high dimensional underdetermined problem that solves the entire 3D volume. We can develop, we have now simple and fast methods for reconstructing the depth if you have multiple masks or multiple measurements, if you can capture that, which means that the acquisition hardware becomes a bit more complex, but that simplifies the reconstruction quite significantly. Depth estimation range is limited to small distances because of the small baseline. It can be improved if you have bigger sensors, or like we discussed, multiple sensors. Portrait illumination, I briefly discussed, but that sounds very promising, that you can significantly improve the quality of reconstruction. And for my some potential direction and challenges that I think about, like one is large area sensing, or sensing when we have these distributed pixels or small sensors distributed on some surfaces which can be flexible or curved, and we want to image that. This last point is one thing that is a bane for everybody who's working on lensless imaging, that noise and ambient light, they are a big problem, and we do not have good solutions to cancel them. So if any of you have some ways to subtract the unwanted light, that can really improve the lensless imaging systems significantly. And other things that I didn't get to it, like how do you improve the reconstruction and priors using data-driven methods. I'm not going to that. Most of our codes are available on these two GitHub repositories, supplemental results as well. Please check it out. And I here on this list, there are some references, some of our papers, some of the papers that I cited earlier. My email, my webpage, if you need more information, please don't hesitate to reach out to me. I have one quick plugin. I am looking for PhD MS students. If you're interested in any of these topics, please contact me. So I'll stop at that. Thank you.
Thanks, Dr. Asif, for this wonderful talk. Any questions from the audience? I have one question. So have you considered the phase information when doing this reconstruction?
Not in this one. This is an incoherent light. Everything is ray optics.
Oh, I see.
Yeah. So yeah, this one doesn't have much to do with phase. Oops.
There's one question from the audience. So is there a relationship between this and LiDAR?
So I guess in the sense that LiDARs, they are used for depth estimation. In that sense, there is some relation. But as I said earlier, LiDARs, I think they have the other thing that they actually start giving good reconstruction beyond a certain depth. So if I'm not mistaken, like if your scene is within a few feet, then it's not very accurate, but it is very accurate for a few meters. So LiDARs are useful for that long distance, maybe depth estimation. These cameras, these lensless cameras that I discussed, small baseline, so they will give you good depth reconstruction in a very, very narrow window, very close to the sensor, and they are really useless for anything beyond a meter if you have a single sensor. So it's maybe complementary to each other, doing depth estimation, but on a different scale. And I don't want to make any claim about accuracy. LiDARs are very accurate. For lensless cameras, it is more of these custom prototypes that we all have.
So there's one question from Euron. So for the learn mask, do you observe a relationship between the learn mask and the imaging parameters or image thing?
Sorry, say it again.
For learn masks, did you observe a relationship between the learn mask and the imaging parameters or image thing?
I don't know which parameters. Hi, Yoram. Can you please say?
Hi, you can unmute yourself.
Unmute yourself.
Yeah.
Yeah. Hi.
Hi, Salman.
Yeah. Hi.
Great talk. So I was wondering, qualitatively, did you observe some role that for, say, bigger sensor, your mask tends to look like this, and for fewer pixels, your mask tends to look different, or some relationship between the imaging parameters of the system or the scene and the type of mask that is learned?
Yeah, that's a great question. We did not try that for a range of imaging scenarios because we had a very specific prototype and we wanted to show that how well the learn mask will work on that. So most of our efforts were, I think, optimized, or the forward model that we use, the parameters were fixed for that prototype in mind. But this is a good question, very good question. That if we have different parameters for that sensor mask, then or imaging setup optics, then what kind of patterns we learn.
Mm-hmm. Okay.
Yeah. Yujing, my student who did most of experiments, is on the call. I don't know if he may have some insight, but if there is something, I'll send it to you.
Okay, great. Now, while I have the microphone, I had another question.
Sure.
Did you try to learn the structured light, structured illumination?
We did. Yes, okay. we did that. I don't have those equations here, but it turns out that if you're doing this coded illumination with multiple shots and whatever is your mask pattern, you get the system you have to solve is a Hadamard product of your operator matrix and the outer product of your mask patterns. And this kind of shifted mask pattern, shifting dots, or any other orthogonal pattern gives us a block identity matrix, and that performs very well. We tried to do this optimization that implement everything in this differentiable method and learn the illumination patterns, or try to make that underlying matrix as close to orthogonal as we can. They don't do any better than shifting dots or other orthogonal patterns we tried.
I see. Okay, thank you.
Yeah, I'll share that paper. We have it. I'll share it with you.
Okay, great.
Yeah. Yeah, thanks.
So I have another question. Is it that for some of the reconstruction results, you have some aliasing effect? Is that due to the model mismatch, that you assume some model of data, but could be some model mismatch?
Do you have any specific example you want to talk about on this one, or was it more on the depth?
I think the depth one. So I wonder what kind of reconstruction algorithm are you using? Are you using like an optimization-based approach, or are you using like an on-road deep network approach?
No. So these are all least squares.
Oh, it's just using optimization.
Maybe with some total variation or L2 regularization.
Oh, I see.
Yeah. So I don't have the result here, but we tried like a unit after this. After sort of whatever reconstruction we are getting, you get a slightly denoised image that you would get if you just pass this image through BM3D as well. you don't improve on the resolution.
I see.
Yeah, but there are some other works from other groups who have shown that if you jointly optimize maybe the parameters of that least squares or train a network to do reconstruction, you get better results. Simulations, everything works very well in simulations. In practice with real data, they don't always give the same quality.
I see.
Yeah, that has been my finding. Like with this light and noise and other non-idealities that we get with real implementation, they are not modeled very accurately in simulations. So that may be the reason.
I see.
Yeah.
Thanks.
Yeah.
Any other questions from the audience? So if no, thanks, Dr. Asif, again for this wonderful talk.
All right. Thank you very much for the invitation and all the great questions. Really enjoyed it.
Thank you.
Thanks.
See you.
All right. Thanks, Jink. Shall we just leave?
Thank you so much.
All right. Take care. Bye-bye.